All right, in this video, we're going to look at transformations, and in particular, vertical and horizontal shifts, and I'll progress through the other types of transformations in other videos. First, I just want to point out that there's a difference between types of transformations. So a rigid transformation is a transformation that does not change the shape of the graph. It'll change location, it may change a little bit of orientation, but it's not going to change the shape. So vertical shifts, horizontal shifts, reflections, and rotations are all examples of rigid transformations. And I have here just an example of a shift, which you can see doesn't change the shape of that graph, just where it is. And in contrast, a non-rigid transformation is one that does change the shape of the graph. And we'll see some of these later, but they include vertical stretches and compressions and horizontal stretches and compressions. And I see here, I've given you an example of a horizontal compression. So we'll start to tackle these one at a time. We're going to begin with vertical shifts and then horizontal shifts. Before we do that, I'm going to use what's called the fundamental graphing principle for functions, which states that if b is on the graph of y equals f of x, then f of a equals b. And that may seem a pretty simple and basic idea, especially if you're coming to this video with a little bit of algebra skills. But it's a very important idea that we'll fall back on, especially when we deal with transformations that seem counterintuitive. In particular, a lot of the transformations involving x values tend to involve, doing the opposite of what you would think. And it's this principle that's going to help us understand that. So I'll be referring to this as we go through these examples. So let's start with some vertical shifts. Let's say we've got this graph down here on the left, f of x, and we have a transformation g of x, which is equal to f of x plus 2. So the first thing I'm going to do is I like to kind of, in a table, give all the information I can. So I'm going to not only put inputs and outputs, but I'm going to, label points and get everything involved. So we know a lot about f. We know all the points. We therefore know the inputs and outputs. So for instance, I know the point 0, 1 is on this graph. I know the point 2, 3 is on this graph. 4, 3, and 5, 5. And of course, if I want to focus just on the outputs here in red, those are just 1, 3, 3, and 5. So now let's talk about g of x. What's nice about transformations involving y values, which this is a version of, usually you can just do them in a pretty straightforward way. So let's just start substituting these x values in for g and see what we get. So I have g of 0, well, that's going to equal f of 0 plus 2, which is equal to, well, f of 0 is 1, so that's 1 plus 2, which is 3. So that tells me the point 0, 3 is on the graph of g. Let's substitute in 2. G of 2 is equal to f of 2 plus 2, but f of 2 is 3. So that is 3 plus 2, which is 5. So I plot the points, so the point on g is 2, 5. G of 4 would be f of 4 plus 2, but f of 4 is 3, so that's 3 plus 2, which is 5 again. So I plot the point 4, 5. And g of 5 is equal to f of 5 plus 2, and f of 5 is 5, so that's 5 plus 2, which is 7. So I've got the point 5, 7. And if you reflect on what happened here, basically our x values are the same, right? These are the same, but our y values went up by 2, right? These are our old y values. These are the y values for f, and the y values for g are 2 more than that, as we can see over here on the right. So when you see the graph relationship, you can see that causes a shift vertically by an amount of 2. And so if we kind of just summarize this principle here, and you'll be seeing I'll be doing this a lot to help us. The fundamental graphing principle says if AB is on the graph of y equals f of x, then f of a equals b. So if g of x equals f of x plus 2, then when x equals a, g of a is f of a plus 2, but f of a, of course, is b, so it's b plus 2. And so that means that the point a comma b plus 2 is on the graph of G, and this causes a shift up of an amount 2. Okay, so in general, now I could have done all that again with, by subtracting 2, but I don't think that's needed. We have a summary here of essentially what happens when you're adding a value or subtracting a value. Notice I said that k is a positive number to help us there. It's just going to cause a shift vertically. And that's just an overview of vertical shifts. Let's take a look at horizontal shifts, which are a little less straightforward. So same graph. I've even put down the points for f to help us. Let's try our strategy we did before. Let's just start plugging numbers in like we did in the example above, and let's just see what happens. So what's g of 0? G of 0 is equal to f of 0 plus 2, which is f of 2, and f of 2 is equal to 3. Okay, so we know that the point 0, comma 3 is on this graph. Let's try plugging 2 in. G of 2 is equal to f of 2 plus 2, which is f of 4. But f of 4 is 3, so we know the point 2, comma 3 is on this graph. Okay, again, so far so good. What about plugging 4 in? So g of 4 would be equal to f of 4 plus 2, which is f of 6. And f of 6 is, well, we don't know, right? We don't have it. It's not in the domain, actually. If you go back and look at the function there, the graph, it's not even in the domain. So that is a problem, right? We have no idea we don't know how to go forward from here. And a similar thing happens when you plug 5 in. G of 5 is equal to f of 5 plus 2, which is f of 7. And again, we don't know what that is, so we really don't know how to plot those points. So this strategy didn't really work for us, and it's actually, we were lucky we got so far, because sometimes it doesn't work even at all. So we kind of have to think of a new strategy for figuring out how the graph of f gets affected by this transformation. So here's our new strategy. I have a different table here. Okay, and what I'm going to claim here is that what we want to do is not to imagine the 0, 2, 4, and 5 as being x. We want to imagine those being x plus 2. So I'm going to copy them here and then talk about why this makes some sense. Okay, notice we know exactly where f sends all of these inputs, right? We know what f of 0 is, we know what f of 2 is, f of 4, f of 5. And ultimately over here, it came down to evaluating, right? Once we evaluated what was inside the parentheses, we knew what numbers f was sending to outputs. So what we really want to know is, okay, if for instance f of 0 is equal to 1, which we know, then what would I have to plug in for x to make the output also be a 1? Well, in order to figure that out, we need to set x plus 2 equal to 0 and solve. X plus 2 equals 0, so that means x equals negative 2. Aha. So if x is a negative 2, that is going to produce, well, let's see, g of negative 2 equals f of negative 2 plus 2 equals f of 0. Oh, but we know that. That's 1. So negative 2 comma 1 is a point. Let's try another point. So I know, for instance, that f of 2 is equal to 3. And if f of 2 is equal to 3, then that means I can, and I also know that I want f of x plus 2 to equal to 3. So that tells me I should set x plus 2 equal to 2, which means that x is 0. So let's use a different color here. right? That would be a 0. And if we check that, we get g of 0 equals f of 0 plus 2, which is f of 2. But we know what f of 2 is. F of 2 is 3. So we plot the point 0, comma 3. So in a similar fashion, I hope you can see at this point what's happening. These values over here on the left are 2 less than what we saw before. So this will be a 2, this will be a 3. And we can check that g of 2 equals f of 2 plus 2, which is f of 4, which we know f of 4 is 3. So we've got the point 2, comma 3. And then, of course, g of 3 is f of 3 plus 2, which is f of 5, which we know f of 5 is 5. So we have the point 3, comma 5. Notice that these, again, these x values are 2 less than our old x values for f. And so the general principle here is that that x plus 2 causes a shift not rightward, but a shift leftward. So you can see the graph plotted, it shifts it leftward. And so if we generalize here, if b is on the graph of y equals f of x, then f of a equals b. If g of x equals x plus 2, note we want this x plus 2 to equal, right? We want that x plus 2 to be what, we want that new x to be whatever we have to plug in order for x plus 2 to evaluate to a, so that f can send a to b. So that tells us that x would have to be a minus 2. So g of a minus 2 is equal to f of a minus 2 plus 2. Let's move this a little bit, which is equal to f of a, which is equal to b. So that tells us the point a minus 2 comma b is on the graph, and that tells us there's a shift left of 2. And just to summarize in general, if h is positive, f of x plus h, all in parentheses, will shift the graph left h units, and that means you subtract h from the x coordinates. Whereas f of x minus h will shift the graph right h units, and you'll add, I meant to say not k, I meant to say h to the x coordinates of the points on the graph of f.